How does a single number dictate the behavior of an entire mathematical space? Whether you are solving systems of linear equations, mapping how grids warp in geometry, or setting up multiple integrals in calculus, all of these operations eventually bottleneck at one single scalar term. Matrices stretch, squash, and rotate space. To do meaningful mathematics in those spaces, we require a rigorous metric to quantify that exact distortion. Mastering this specific scaling factor is the requirement for advanced multivariable mathematics. Without a mathematically flawless definition of the scaling factor, the calculus of multiple dimensions collapses. We find the purest treatment of this problem in Chapter 9 of Walter Rudin's Principles of Mathematical Analysis. Rudin explicitly places linear transformations immediately prior to tackling functions of several variables. His approach is strictly axiomatic. We have to build an airtight framework from scratch before we can address theorems like the inverse function theorem. We will rigorously define the determinant algebraically, and then translate those abstract rules into their geometric realities. By abandoning raw calculation in favor of Rudin's structural proofs, we uncover the geometric nature of the determinant. We begin with an axiomatic setup. What properties must a volume measuring function possess in n-dimensional space? Our subject is the square n by n matrix. Volume transformations require the input and output dimensions to be exactly equal. This formula is the algebraic definition of the determinant, summing all permutations of 1 through n. The term S of pi is a signature, assigning +1 for an even number of element swaps and -1 for an odd number. This permutation notation is highly abstract, and it requires a bridge to actual computation. We construct that bridge using the mathematical minor, defined as the determinant of the remaining submatrix when a row and column are removed. This brings us to the Laplace expansion formula, allowing us to travel across a row, multiplying elements by corresponding cofactors. This sign-switching algebraic engine is the way to guarantee our volume function behaves as expected across any dimension. Let's shift from abstract n dimensions down to a specific 2x2 matrix to test this algebraic engine. For a 2x2 matrix cofactor calculation, we multiply the primary diagonal, a times d, and subtract the secondary diagonal, b times c. Geometrically, these columns represent basis factors on a Cartesian grid. The resulting parallelogram has an area exactly equal to AD minus BC. Now we scale the complexity to a 3x3 matrix expansion. During a 3x3 cofactor expansion, you must account for the mandatory negative sign on the middle element, dictated by the signature of the permutation. In three-dimensional space, the three column vectors form a parallelepiped. Its calculated interior volume equates directly to the determinant. This introduces the concept of signed volume. Swapping two vectors mathematically results in a negative determinant, representing a literal flip in the spaceless orientation. The alternating signs in Rudin's definition are instructions for tracking spatial orientation. How do we formalize this geometric behavior back into pure algebraic axioms? We define the determinant as having multilinearity in the specific context of matrix columns. This equation shows the determinant operates linearly with respect to any single isolated row or column, while the others are held constant. Next, we define the alternating property of the form. If you swap any two adjacent rows or columns, you negate the overall value of the determinant. The consequence of this alternating property is inevitable. Any matrix containing two identical rows or columns must evaluate to a determinant of 0. The determinant is the unique alternating multilinear n-form normalized to the identity matrix. Let's apply these foundational properties to standard matrix transformations to prove their utility. Theorem 1 shows adding a scalar multiple of one row to another preserves the determinant. The space shears, but total area remains constant. Theorem 2. The determinant of any triangular matrix is found by multiplying its main diagonal entries. Here we see Theorem 3, the multiplicative property, stating that the determinant of A times B equals the determinant of A times the determinant of B. The volume scales cascade sequentially. Theorem 4 establishes the invertibility threshold. The determinant of A equals 0 if and only if the matrix columns are linearly dependent. A zero determinant mathematically signifies that the geometric space has suffered a collapse into a lower dimension, destroying its invertibility. We pivot from pure linear algebra back to Rudin's primary objective in Chapter 9, analyzing functions of several variables. Calculating derivatives for complex nonlinear vector fields is difficult, but at a microscopic local level, they can be approximated by a linear matrix, the Jacobian. Taking the determinant of this Jacobian matrix provides a determinative test to see if a multivariable function is locally invertible. This mechanism provides the structural basis for the inverse function theorem. Our algebraic buildup serves as the essential framework for the calculus of multiple dimensions. We have defined the dual nature of the determinant. It is an abstract, alternating multilinear form that measures physical volume scaling and orientation. A determinant of 0 represents a non-invertible dimensional collapse. The determinant acts as the bridge connecting rigid algebraic logic to tangible geometric reality in advanced mathematics. Subscribe, like, and comment to support more in-depth chapter-by-chapter breakdowns of classic mathematical texts like Baby Rudin.